Okay. So good morning to everybody. So the title of the talk might be a little bit misleading. Okay. So typically such a title would correspond to a talk given by a theoretician explaining you all the physics potential of a large accelerator like the LHC. So that is not the case, because either I'm not a theoretical physicist, nor that's the scope of this workshop. Okay, so essentially you should intend this title as for challenges for anomaly detection at the LHC. Okay, so I got a couple of slides with a couple of let's say disclaimers, if you want. So the first one is about what means to do statistical data analysis in LHC physics. And I start with this sentence by Rutherford, which claims that if your experiment needs statistics, essentially you need to do a better experiment. So if you want to reinterpret this sentence with a modern view, that would mean like what matters is the experiment. The data analysis is something that is just bringing you to the conclusion, just putting things together, and it's somehow an obvious step. So my point is that I'm not really sure that is the case. Actually, I'm actually sure that that is not the case if right now. The data analysis plays a crucial role in physics nowadays, especially in high-energy physics. Okay, so the other slide that I have, if you want, of general, somewhat a general comment, is about a statement, if you want, a cornerstone of information theory. Okay, so we're going to talk about anomaly detection, and but in doing that, we should always remember that in order to do inference, so infer information from the data, but also to do data compression, you have to make assumptions, you have to make hypotheses. Okay, so both for doing data compression or data reduction, which is essentially the same thing, or to do inference, you have to make hypotheses. You cannot live without that. Okay, and this sentence is taken from David McKay, and I encourage you to read this book about information theory, which is a very good one. So there is a very famous sentence, which is let the data speak for itself, which is true, right? I mean, you can try to take the most out of the data without being biased, but you have to keep in mind that you have always to make a question, right? So you have to interrogate the data can answer, but you have to make a question. So depending on the question that you ask, you can get a meaningful answer or not. Yet another disclaimer. I'm a physicist working at CMS, which is one of the two omnipurposes at the LHC. So most of the things that I'm going to talk about refers to CMS, even though the other experiment that is taking data at the LHC, which is Atlas, essentially all the things that I'm going to say refers to that in the same manner, essentially. Yeah, so I don't know whether everybody is familiar with that, but essentially LHC is a big particle collider placed in Geneva at CERN, and we have actually 4 experiments, not just, actually even more than that. So we have a few experiments. 2 of them are so-called omnipurposes. Okay, so essentially they are meant to look for all sorts of physics that is there. There are other 2 experiments that look at the collisions, which are dedicated to other things. Yes.
Since you're pointing out that everything you're going to say applies to CMS and Atlas, can you try to point out side by side even the differences with LHCb?
Yes, yeah, I actually have one slide on that.
Thank you very much.
Okay. So, what's the status at the moment? So essentially, the LHC has been extremely successful in doing what it was supposed to be doing, meaning finding the Higgs boson. Okay, so we did find the Higgs boson in 2012 after 2 years of running, and so we are very happy. But to cite the former director of the research at CERN, we are currently suffering from this disease, which is PHD, post-Higgs depression. in a sense, the LHC was also supposed to explore the energy regime where plenty of other things were supposed to be. Okay. So let me mention, I'll discuss a little bit how we do that kind of exploration. So essentially, what we do is that we go to a theorist, we ask for a beyond the standard model theory. We generate Monte Carlo samples with that signal in mind. We check for standard model processes that can mimic that process, that signal. We also gather those Monte Carlo samples. I mean, Monte Carlo samples for those the standard model processes. We check whether our online selection, I'm going to get back to that in a second, are efficient for that given signal. If there is not, we're going to update our trigger selections. Then we optimize the analysis in order to maximize our sensitivity to that given signal. We apply, once the strategy is defined, we apply the strategies to the data and we get the result. If something is not compatible with standard model, typically we get back until everything is fixed, and then we publish the result. So we are somewhat stuck in that loop, okay? And the fact that I actually coded quote unquote in a Jupyter cell is not because I want to be funny, actually quite the contrary. The fact that there are actually people trying to optimize, let's say, to automatize all these steps. I tell you, there are people that are trying to optimize really all these steps, okay? That is not a joke. It's actually quite sad because it means that the ingenuity that you need in order to do these things is going down, okay? So that's the results. Actually, that's a short list of all the analysis and the publication that we have done in search for alternative hypotheses with respect to the standard model, okay? So of course, this is not meant to be read. It's just meant to impress people about how many alternative options we checked. And the case is that none of these hypotheses resulted to be more favored by the data with respect to the standard model, okay? The other sad thing, if you want, is that it's not that we really falsify those theories. We actually place limits on their parameters, okay? Essentially saying that the scale at which those theories might apply are higher than those explored at the LHC, probed at the LHC, okay? Okay, now let me get back to something a little bit, okay, I don't want to be controversial here. I'm actually citing Luis here, which is taken from a lecture by Kyle some time ago, which the sentence summarizes the two attitudes. So essentially frequentist, which is, let's say, the approach that we take when we statistically analyze our data, using pickable logic to deal with issues that are of no interest to anybody, okay? Instead, Bayesian, they address questions that everybody is interested in by using assumption, at least Luis said, that no one believes. I respectfully slightly disagree with that. I think that by assumption that not anonymously are believed in, okay? About this thing, I actually encourage you to check the lecture that Glenn Cowan gave here at GGI a few years ago, extremely good ones, and especially the last minute of the link that I have there, where Glenn is actually telling the story about how much is he concerned with the CERN press office, that all the times that the experiments publish the results, they get it wrong. They communicate that in a wrong way, saying that instead of saying that, you have to think about it, because so the data, so under the hypothesis of the standard model, the probability of the data of being as discrepant as we found, or more so, is blah, blah. How can you imagine a press office to communicate a scientific result in that way? That is not what we need. We need, let's say, the plausibility of an hypothesis given the data, not vice versa, okay? The problem here is that, of course, you need what is called as prior, okay, which is essentially our subjective degree of belief about that given hypothesis, okay? So I don't want to, as I said, I don't want to discuss this whole thing because that's an endless discussion. But the thing that if you have to take decisions, you have to apply this kind of attitude, to your results, essentially. Okay. And so actually part of this in the next few slides, I'm actually trying to revise, if you want, this ancillary information that you need in order to get yourself a subjective plausibility for a given hypothesis. So I'm going to revise these auxiliary informations, if you want, in order to answer the next slide questions, okay, which are the relevant ones. So we saw so far that all the tests that we have done favor the standard model to all the alternative hypotheses we formulated so far. So of course, what you really care is whether are phenomena not described by the standard model being produced at the LHC? Are there plausible alternatives models that have not been tested? So there are still things that are worth testing. And even more, could have some new phenomena gone undetected at LHC? Okay, so in order to answer that, you need to, to have your own personal opinion about the plausibility, okay, about the essentially the hypothesis that some new physics might appear at the LHC or not. So the thing is that if the community opinion about all the answers to these questions is no, so there's nothing at the LHC concerning new physics, we better shut off the machine and exploit the physics program related to the Higgs boson by substituting the LHC with a cheaper machine, the plus and minus in the same tunnel, and doing Higgs physics in that way. Okay. Instead, if the answer is yes, so if you believe that, if your degree of belief, the community believe about the answer to this question is keen on allowing a yes, then we better change our way of doing things, apply machine learning, and let's say move on with respect to the current way of doing things that we have at the LHC. So in the next few slides, I'm trying, as I said, to formulate a little bit better what are my personal understanding of the ancillary information that you need in order to get yourself an idea about, let's say, the hypothesis behind the questions that I said before. So the first one is a slide that I took from Professor Ting that got the Nobel Prize for discovering the JSI. So he's used to show this slide every time he makes a talk. But this is quite relevant indeed, because it actually lists all the experiments that discovered new physics in the last, let's say, in the second half of the last century, and demonstrating essentially that the experiments were meant to do something else with respect to the the physics topic that led to a major discovery. Okay, that was the case for the PS, for the 30 GeV proton accelerator at Brookhaven, for the E plus E minus at SLAC, and so on and so forth. So every time, apparently, this is quite astonishing, the fact that people were designing an experiment to do something, and in the end they made a discovery in a completely different, let's say, in a completely different subject. Okay. The other thing that I want to mention, so sticking to the JSI, okay, so I don't know, whoever is not familiar with the particle physics should know that the November 1974 is known as the November Revolution, okay, because the discovery of JSI was considered, really a revolution, okay, in our field, because came essentially completely unexpected. Okay, so there was a machine, the ancestor of the LHC, the first proton-proton collider at CERN. Okay, it's called the intersecting storage ring. That's a picture of that. And there is this nice paper from 1980, so 60 years after the discovery of JSI, that there were this group of people that made the calculation and estimated that at that machine, with the luminosity that the machine was providing, would produce of the order of 1,000 JSI into leptons per year. Okay, so thousands of events with 4% of background. So a kid would have seen that. Okay, what's the weird story about that? Is that machine operated since 1971. So they got thousands of JSI events 3 years before the discovery of JSI itself. How that happened? Because they didn't look into that. So the experiment was there, but the analysis wasn't right. Okay. They didn't chase for that signal, and they didn't find it, and they lost the Nobel Prize. Okay, now coming back to what I mentioned before, so we are talking about the so-called omnipurposes experiments at the LHC. So I mentioned in CMS, Atlas is very similar. So they were conceived in the early 90s, okay? So you can read the letter of intent or the technical proposal. The technical proposal is from 94, so they started writing it in 92 or something. And you can, 30 years old, right? So you can clearly see there that omnipurpose is not exactly right. So the design of the experiment was meant, well, let's say it was decided on the basis of a well-defined goal, which is to find the Higgs boson in its main decay channels. So X to 4 leptons for the high mass Higgs hypothesis, X to 2 gammas, 2 photons in the low mass hypothesis. So everything was designed in order to, to achieve those goals, okay? So as usual, there was, CMS is made with this onion-like structure, okay? And the assumptions there is that whatever is produced by the LHC in the final state has standard model particles, okay? Then also, let's say the other thing is that they aimed for a 4-pi detector, meaning that you want the detector to be hermetic, nothing should escape, so the acceptance should be very large, but they done that for neutrinos, not for dark matter, okay? This is 30 years old, right? The trigger and data acquisition system, which is one of the main topic of this talk, were designed on the basis of the electronics that were available back then. Okay, so 30 years old. Okay, and they had in mind a long list of new physics models to be sought for, especially SUSY. So let me mention the features, let's say the characteristics of this experiment. So starting from data acquisition and selection. So the data throughput is gigantic, okay? So we have 80 million front-end channels that we read. The size of a single collision recording is of the order of few megabytes, okay? With zero suppression, okay? We collide, the LHC collides at about 40 megahertz, so 40 million collisions per second. And if you multiply the second and the third row, you get with a throughput, you get out a throughput of data, which is of the order of the worldwide internet traffic. Okay, no kidding. That's 100 terabytes per second, is roughly speaking the same internet traffic in 2018. Okay. So how do we deal with that? We do apply, of course, we need to process the data and to select on the basis of what we process. So beyond the fact that you need to put fragments coming from all over the places into a single event at 40 megahertz, which is a extremely complicated task, people regard it as technically not feasible, but also pointless to permanently store the data that the LHC is producing. So we ended up having a tiny fraction of events that are recorded, okay? Of the order of 0.002% of the events the LHC is producing are looked at, okay? Everything else is discarded without even looking into that, okay? Which means that we need to apply a priori defined selection rules. So we need to be biased in what we look at to do our studies, okay? Because the fraction that we save is extremely small. Everything else is thrown away on the basis of predefined, our, if you want, bias, our prejudice. So how does that work? So we have two steps, okay, that Atlas is similar. Essentially, the first step goes from 40 megahertz to 100 kilohertz, and is based on dedicated and match courses, dedicated electronics, match courses data only from the outermost part of the detector. Okay, essentially we have 3 microseconds to take a decision, so we need to be very fast. Okay, and that depends on, because the data, why we look at this, let's say, subset and fragments of the detector data, we keep the whole payload on buffers, and the depth of the buffers allows you to take 3 microseconds to look at every single event. In the end, we actually have a very poor understanding of what's going on. Okay, we have to say, yeah, maybe there is a muon, maybe there is an electron, something like that, but we have a very, very poor view of what's going on. Okay, the second step is a finer step, if you want. It's based on full granularity data and brings from 100 kilohertz to a few hundred hertz. Okay, and it's based on offline quality reconstruction. And then we essentially have 200 microseconds to look at the data. And actually, that is quite annoying. The last sentence is a very important one. Essentially, we do have of the order of 1,000 selection criteria. Okay, it's not that, say, as soon as we have a muon about 20 GeV, we are good enough to take the data. No, we don't have few selections criteria. We have 1,000. Okay, because essentially every single model we test requires an hypothesis in order to be efficient with that signal. Okay, so if you aim at a signal which is not present, if you want, is not entailed in the configuration that we run online, very likely the efficiency for that signal is very low. Okay, so that's just to say that this is a usual picture that people see when they have to describe, when people have to describe how the experiment works. Essentially, we have to get from signals released in the subdetectors to candidates for the physics object we have to look at. So if we see deposits in the calorimeters, and that deposit is associated with a track, then that thing could be an electron. If we see just a deposit in an electrocalorimeter without a track, that would be a photon, and so on and so forth. The whole point is that the detector is providing data at, every single collision is over the order of a few megabytes. But in the end, what we do is that we look at a single float. Okay, so a few bytes. So this is the plot that shows the Higgs boson. So the pinky structure there is the Higgs boson, but that is a single variable, so a few bytes, starting from several megabytes. So you have a data compression factor of the order of 10 to the 6. Okay. So this whole thing is somehow centralized. And again, a huge amount of assumptions are taken. Okay. You have to start from of the order of a few megabytes, and then you have to go through all these steps. Essentially, you have to reduce the data by moving from this data format to a data format which allows physics analysis. But all these steps, you are reducing data. And as I said at the beginning, whenever you do data compression, you have to formulate hypotheses. Okay, and if the hypothesis is the wrong one, you get it wrong. Okay, so actually, this, just for completion, this is the format that is used for, let's say, make our data public. And I tell you that it's completely non-intelligible. I don't know really how can people look at those data if you're not from CMS. Complete mystery. In fact, that's not the case. People typically have an CMS expert joining in, helping to understand what is in the data, and then try to draw a conclusion from that. The last format is this nano OD, and I tell you, this is super small. Okay, a lot of stuff is going on here, and everything is centralized. So if you want to get back from, let's say, to recover some information that is lost over there, then it's essentially impossible. Okay, because this whole thing is taken care of by our superpower computing system. So the single user cannot do that. Okay, so in the end, you actually even further reduce this, and that's essentially analysis specific. So there are many assumptions in the reconstruction process, not just in the trigger. That's my point. So when you are reconstructing your data, when you're trying to get sense of your data, not just when you're filtering it. So when you're trying to make sense of your data, you do take a lot of assumptions. So first of all, charged particles are helices in the detector because of the magnetic field. So there's no bending in the other direction. Particles, they travel at speed of light, almost. Okay, and we always assume that whatever belongs, so only what is instantaneous with the collision belongs to the collision. So if something is happening later, we completely have no clue, or there's no possibility for us to recover that. But that is if you want a reconstruction level, but many assumption occurs also at the front end level, if you want a detector level. Okay, because in the way you apply zero suppression, in the way the analog signal is integrated, in the way you apply local trigger tricks. If you have questions, I can answer that about that later. But let's come to anomaly detection. Okay. So that was just a premises about the fact that indeed we have been taking for the last 12 years many assumptions in pre-processing our data, okay, prior to the analysis, in filtering and processing analysis, the data. So if you want, anomaly detection came in as a major activity, a few years ago. Okay. Essentially, I would classify anomaly detection as a way out of the scheme where you have two hypotheses. H0 being a standard model and H1 being a physics motivated alternative hypothesis. So if you want to get out of the scheme, you go for anomaly detection, quote unquote. And then of course, I actually put here, a review that essentially trying to classify all these anomaly detection algorithms on the basis on how much you rely on theory for the standard model and for the alternative hypothesis. Some of them are completely heuristic, some other rely on standard model and so on and so forth. Gaia and Marco especially will mention a concrete example later on. So I want to stress the fact that you have to question yourself about how powerful is your anomaly detection scheme. So the first one that I would mention is imagine that we had no other idea about the Higgs. Okay, can your anomaly detection algorithm find the Higgs boson without being told to look at it? So far, nobody succeeded in that. Okay. What kind of input does the anomaly detection requires? Okay. So where in the chain that I showed before, your anomaly detection can be plugged in. Okay. So how many variables, how large the set can be, how sparse the variables can be. The other thing that you have to answer is, how does your anomaly detection compare with a physicist just, randomly checking the data? Okay, so there are plenty of physicists who are just like, let me check this final state without any specific hypothesis. Let me check it. Okay, so how does your automatic anomaly detection compares with that? And furthermore, can your anomaly detection machine run online? So it is looking at single events. It's looking at batch, how large are the batches, and especially how low is the evaluation time. Can it actually be run online? So the fact is that presently, all the algorithms that I'm aware of have rather severe limitation in several of these aspects. So if you want, you can ask yourself whether this can be, looking for data at the LHC, the analysis of data at the LHC can be posed as a data science problem, meaning that, I'm always impressed by this picture here, where you have, people trying to end in this huge stuff, which is a 5 megabyte hard disk, okay, in 56, and now you have, actually this is 100 terabyte now on your finger, okay. So I think that if you ask those people in 56 whether you have a factor 10 to the 12 in storage capability, some 60 years later, they will say, no, that's impossible. So can you actually translate this data analysis problem at LHC as a data science problem? So just to state the problem, that would be of dealing with a data set consisting of 10 to the 6, 10 to the 7 features, okay, unlabeled for a 10 to the 15 data points, okay? So that would be the data science problem. So of course, at the moment, that cannot be done, okay? Neither technically nor algorithmically. But is that really the way we want to proceed, okay? The thing is that our domain knowledge, the fact that we know physics, especially in the macroscopic world, we know physics very well, okay? So we cannot really say, let's forget about it and proceed as a data scientist. That's not the way to do that, okay? We need to rely at least partly, okay? And for that, we need the support of theoreticians in order to see what are the hypotheses that can be lifted, what are those that are do not make sense to be lifted, and so on and so forth. Nonetheless, we need to rush to move from here to there. So we need to work on those technical aspects, okay? So what's coming next? So the LHC is going to take data for a few years in the same manner, and then the machine is going to be refurbished, and we're going to get a factor 2 in luminosity for the next 10 years, okay? With a delay of a few years because of the pandemic, war, and so on and so forth. So when I heard about that, as everybody else, we thought, okay, that's pointless. A factor 2 in luminosity does nothing. If you know about the machine, you know that if you work on the availability of the machine, you get the factor 2 as well. Okay, so why to spend $1 billion to refurbish the machine? So this factor 2 might be seen as a little bit depressing. But that's not the case. You should not think about high luminosity LHC. So if you want the next stage of the LHC as a new machine, the machine stays the same, even though the luminosity is higher, but doesn't matter. What matters is the fact that we're going to have new experiments. Okay, and we're going to have new subdetectors, which is very important. But what is really important is that we're going to have new trigger systems. Okay, so we're going to move away from this 30 years old approach to data processing and exploit all the new technology that has been produced in the meanwhile. Okay, so essentially, I have little time, but I don't want to go too into the details. But we're going to have longer time. We're going to have essentially the same offline quality for, let's say, interpreting the data at 40 megahertz. Okay, so from understanding nothing what is there, we're going to have something. We're going to have electronics which are going to allow us to reconstruct tracks, vertices, particle flow, which is a special technique that we use, and so on and so forth. So essentially, we're going to have offline quality understanding of the data for every single bunch crossing, every single collision. Okay, so in order to do that, we're going to deploy machine learning algorithms. Okay, on those kind of electronic boards, okay, on FPGAs, okay, which is, I think, probably the most important task that we experimentalists have in the next years. So this is answering the question about what about LHCb. LHCb, actually, there are other experiments which are already doing, if you want, a triggerless analysis. The thing is that the other experiments do exactly know what they have to chase, okay? So the hypothesis that they make is not under discussion. Okay, they have to do B physics. You know exactly what you want to do, and that's why if you exploit technology, you can get there without this much of an issue. It must be said that also in the past, we actually run this, if you want, online analysis in CMS and Atlas, but at the HLT level. So the second step when we have the full granularity, but that still is, a small portion of the data that we have. Okay, so attached to this new scheme for the trigger, which I don't want to discuss, the idea is to indeed attach a system which allows not just to reconstruct, but also to analyze the data that, let's say, the reconstruction that we produce at 40 megahertz. So we want to put together a triggerless analysis facility. So if you want to at least to remove the bias that we have by selecting with predefined selection, let's say, concepts, the data that we look at. Okay. So this is a list that you put there if you want to impress your theory colleagues. I don't want to go into that. Essentially, we do have all the technology that especially in 10 years from now, we're going to have everything that is needed in order to achieve that task. Okay, and I want to mention the fact that all this stuff, this triggerless analysis facility, is already under test right now. Okay, the thing is that we do have also results, but they are still to be approved by the rest of the collaboration. Okay. So the other important thing is that, especially for students, if you want, is that we do need to have the entire pipeline to be adopting advanced solutions. Okay, so not just electronics, also if you want the processing with computers and all that. So you need to, let's say, endorse and exploit, if you want, generic data science tools, big data tools, and so on and so forth. Okay. So profiting from developments that are done in other fields. Okay. I mentioned the fact that the reconstruction is assuming a lot of stuff in order to produce these physics candidate physics objects. Okay. So what if we actually read out the data and process data without even applying any reconstruction? So that is also being tested. So part of the muon spectrometer is currently read out at 40 megahertz. So we get everything without any bias, even no reconstruction done apply on that. Okay, and we are doing that now. It's quite interesting, and the finding that we get from this study might actually push the need of applying that kind of scheme to the rest of the detector as well. So the take-home message and the next steps, I actually think that even after all the null hypotheses that all null tests that we have conducted so far, my personal belief is that new unexpected physics might still be there to find at the LHC. we might be limited by the super large amount of assumptions that are there. So our sensitivity might be limited by that. So it is necessary to profit from the current and future developments in technology and science, so meaning like machine learning and all that, to move ahead from a scheme that we've been pursuing for the last 30 years. Okay, we were running the experiment in the same manner for the last 30 years. Okay, so I suggest people to look at this high luminosity LHC, this new phase, as an opportunity, especially the upgrade of the detector, especially in terms of what I called triggerless analysis facilities. So the to-do list. So as I said before, experimentalists and theorists should sit together to think about what are the things that can be lifted when we look at the data, and what that implies from the experimental point of view. Okay. We need to, of course, work hard, and people are doing that, to improve the performances and the scope of the anomaly detection algorithms. And last but not least, you need to, oh no, too bad. We need to learn to program VHDL. Okay, this is especially for students, or at least HLS. Wow, sorry, this is rotated. So this is just to introduce the next speaker, which is so that's a cartoon that she made. Essentially, if you have to feed the anomaly detection a picture with all those faces, the anomaly detection is going to look for, typically it's going to look for an anomalous face, okay? Because you are providing faces, and you're actually telling the anomaly detection algorithm to look for faces which are anomalous. But sometimes it's not in the faces that new physics is sitting, okay? In other features of the data that you're looking at. Okay, that's it. Thanks a lot.
So thank you for this nice presentation. Questions?
Thank you for the very interesting talk. I'm certainly impressed by the trigger slide. I was wondering about if you wanted to run an anomaly detection technique on a trigger. How future-proof is that, and how can you be sure that you are not relying too much on a certain choice of, let's say, for instance, a few years ago, we knew that we thought that the autoencoders were perfect for anomaly detection, and now we know that they are not so good because they miss certain types of anomalies, so they're not really able to tell apart. Let's say if I train on tops, they think QCD is the same as top, and that's something we only know after a lot of work with the anomaly detection. How can we be sure if we implement it now that it will be future-proof in some sense?
I don't know. I have no idea. That's the point, right? I mean, my point is exactly that. I mean, we need to view the future developments. Let's say we need to work in order to, let's say, under the assumption that those things might be needed to be run online. That's my personal view. Okay, because online, because essentially the storage issue is still there. So even though we managed to process data at 40 megahertz, let's say at full rate, still it's feasible to store everything, right? Because that would be exabytes of data. Okay, there's no point doing that. So you need to work online essentially. So your anomaly detection algorithm should be capable of dealing with that. So in terms of processing time, but also accuracy and everything, depending on what is your strategy, whether you want to work on batches or, let's say, or on accumulated stuff and so on and so forth, or you want to produce intermediate objects that you want to analyze later. So these kind of things have to be considered when you work on algorithms. Okay, that has to be part of the job. Of course, I mean, you should still doing the usual approach of running your anomalies detection also on offline data, for sure. I was just saying that the online part should be considered as well. And I'm saying that because I'm trying to convince my colleagues that that's the case, right? Because these triggerless facilities are super interesting, but the amount of work that is being put there is still limited. Okay, and I think that both experimentalists and the theorists and whoever is developing machine learning algorithms should work with that in mind. Okay, with issues like that, the fact that you might have something that works in one case, not in another, but especially in the online environment, they should be robust. Okay. Dimmi.
Okay, I think we are over time.
A little bit.
So it's better to postpone additional questions